All right, so going over the warm-up, we have 4 similar but different problems. When you see, and they all the same thing, x squared plus number on the bottom, 4 different approaches to 4 different problems, really 3 different approaches. So the first one, when you have just number over x squared plus number, does anyone know what type of a function it's going to be? It's going to be an arctan, right? This works. Okay, and so there's your answer. Make sure you do the 1 over a out front for an arctan. Right? So any questions on the arctan? Okay, the next one, when you have an x over an x squared, what method? Oh, yes?
Would it be 4 9?
You take the square root of what's here, that's your a value. So this is like, if you think of this as x squared plus a squared, then it's the a that goes up front, not the a squared. Yep. Good. Okay, so the next one you have an x over an x squared. Does anyone know what method you have to use for that? Yes? A u sub, right? So you do a u sub and you end up with a natural log. You can have the absolute value, but since it's x squared plus 9, you can also drop the absolute value because the argument's always positive, right? So either way is fine. All right. Now we're up to x squared over x squared. 2 methods that you can use. One that we, Mr. Thomas and I prefer, but there's another one that's perfectly fine. So can anyone tell me a method? Long division, good, just shout it out, that's fine. So long division, that's the way that I normally approach these, right? Long division. The other method is you could do what's called a special case u sub, where you let u be the bottom, and then you'd have to solve for another x. You'd get it in terms of an x, and you'd have to solve for x. You'd have a square root thing, and you'd have to put it in the top, and sometimes it doesn't even work, right? You just make a mess. So that's why long division is usually your best bet. So long division, you end up with that. And then the final one, x cubed over x squared, again, what method are you going to do? Long division. Whenever this degree is greater than or equal to the bottom, right, you're going to do long division, and you end up with that one. All right, so you had to do a little bit of u sub on this guy, like to get to there. So just because it's long division doesn't mean it's going to be simple. Sometimes you still have to do u sub to find the final answer. Any questions on any of those on the warm-up? All right, then let's start in with the lesson. So today we are doing section 6.1 part B, which is Euler's method. Euler. Does anyone remember anything about Euler? Yes? He has a what?
A line?
He has a line named after him.
We did that in geometry.
Oh, okay. Anything else? Okay, and I get them mixed up too. Was Euler the one who had to move to Russia because he was a friend of Bernoulli and ended up being like head of the mathematical department of the Academy of Russian Sciences or something like that? Was he the one who had all of those children die? He had like 5 of his kids not live through past childhood. Really sad life.
I don't think it was Euler.
That's not Euler?
I don't think so.
It's a look. I'm trying to remember. I don't remember. Maybe that was Riemann. I don't know. Anyway, we'll maybe we need to go back and double check our history. So, all right, but Euler's method. Euler's method is a lot like Newton's method. So if you remember Newton's method was a way of approximating zeros of functions. The way you did Newton's method was you had some x value where you started, and then you found the equation, the tangent line, and you found where that intersected the x-axis. That gave you your next x value. You took the next x value, plugged it in, found the next tangent line, found where that intersected the x-axis, right? And then that gave you the next x value, and then you found the next tangent line, and you just kept doing it, right? Each time you run through that process, it's called an iteration, right? Most of the time with Newton's method, we don't do more than 2 iterations, right? Once in a while 3, because the numbers get kind of messy, right? A lot of decimals. Euler's method's the same way, right? Yay! Okay, so anyway, lots of decimals today. Euler's method, you're going to use tangent lines again, but this time you're going to use tangent lines to approximate the solution to a differential equation. So they'll give you a starting value, and then they'll give you like a distance to get from that to the next x value. So the equation isn't determining the x values are given to you right at the beginning, and then you just keep plugging them in and finding tangent lines, and kind of they walk along the solution. So I'm going to show you what this looks like. All right, it's your favorite software. Yay, GeoGebra. Just a moment, it's loading. There we go. Okay, so the red lines, those are the true solution to some differential equation. And what the, let's see if I can move this. There we go. Okay. And then these little dots here represent the approximations to the solution of the differential equation. So what's going to happen is when you have a problem, you're going to get a starting value. In this case, it's where the point A is. So you get a starting value. You'll be told how many times to do this. This n represents the number of iterations that you're going to be doing. So on this program, they use 27. So if we kept moving over, you'd see 27 dots, and then it would just stop, right? So, and it doesn't matter. You can do less, you can do more, but it's not going to change. It's just how far out it goes, right? The h is like our delta x value. It's the distance from one x value to the next. The x values for Euler's method will always be evenly spaced. So, and they'll have to tell you what h is. If h gets really big, then the solutions are farther apart, and you end up with a less accurate approximation, right? So, as the solutions, let's see if I can move this over a little bit, right? So there's your solution curve. So as the farther apart the h's are, the less accurate the solution curve becomes. As the h's get closer together, the approximation is much more accurate compared to the actual solution, right? So, but the problem with the h's being closer together is the decimals get uglier, right? So if you have a step where your delta x is 1 and you're just plugging in integers, life is easy, right? But when your delta x is 0.2, then the decimals get finicky. So, but you get a more accurate solution. All right, so that's basically what we're doing today, is we're going to be finding the values of these dots. And those dots are basically solutions that would closely follow the actual solution curve. All right, so we're going to slowly walk through an example. Similar to Newton's method. I don't know if you remember Newton's method, but there were two ways to do them. One way was to just sit there and walk through by hand. Find the equation of the tangent line, find the x-intercept, find the, plug that into your function, get the next x, y slope, find the next equation of the tangent line. And you just keep walking through it, right? I like that way because it's easy to remember. It's a process. The other way to do it was there was a formula and you made a table. I don't know, did Mr. Thomas teach you the formula with the table method? No? Okay. Very few of my students used it. I think maybe 2. So it's not, it's hard, it feels easier when you're doing it, but the problem is come May, you're not going to remember. So you'll probably remember the process, but it's hard to remember some formula. What formula did I use to make this table thing? So I prefer learning the process over learning a formula. But I'm going to show you both today, just so that you can see the two alternatives, right? So we're going to start with this differential equation. So suppose y prime or dy dx equals 2x plus y. If y of 0 equals 1, that means our initial value, our initial point is 0, 1. X is 0, y is 1. Approximate y of 1 using Euler's method with a delta x of 0.25. So I'm going to move this down just a tad. So if we have to figure out the x's that we're plugging in, move this up. So the first x we'd plug in would be 0, which is actually given. right? We already know the y value, it's 1. What would be the next x value that we would plug in? 0.25, because that's our delta x. It's like kind of what we're walking by. What would be the next x value that we would plug in? 0.5. Then what? 0.75. Then what? And then would we keep going? No, we would stop, because that's what we're trying to approximate is y of 1. Right, so once you get to an x value of 1 and you plug it in, you're done. 1 is done. Right? Okay, so here we go. The steps for doing this, first step is to write an equation of the very first tangent line. So the point is 0, 1. The slope you get by plugging into your differential equation, because remember y prime is slope, right? So we plug our point 0, 1 in and we get our slope. So I'm going to take a second, write the equation of the first tangent line. Alright, so your first tangent line should be something equivalent to y equals x plus 1. Everyone get something equivalent to that? Good. What do we do with this? We're going to take our next x value, which is 0.25. We're going to plug it into our tangent line. That'll give us the next point. And then we're going to use that with our differential equation to get the next slope. And then we're going to write the next equation of the tangent line, right? So we get our first equation, we plug our x value in to find our next point, and then we use that point with its slope to find the next equation of the tangent line. You will definitely need a calculator, so if you don't have your calculator right, you might want to get it out, because there's going to be a lot of decimals today.
I'm sorry for this interruption, but we are in a situation where we're looking for a student. It is Jacob Ferris. Staff, if Jacob Ferris happens to be in your classroom, would you please call 58040, 58040. Thank you.
So once you get your next tangent line, then you plug in the next x value, right? So your next tangent line, so you've got your point, you've got your slope, there's your next tangent line, and now you've got, once you've got that, now you're going to plug 0.5 into there to get the next point, and then use that to get the next slope, and then you write the next tangent line. And you just keep on going until you finally end up with the x equals 1 that you can plug in. So everyone see if you can take this all the way to the end. Tell me how you got this slope. So are you sure? What do you already know you get that? speak too, right? Then you can talk to the person next to you.
Oh, I'm so sorry.
Did you drop it? That's what usually happens when you drop these, they get those spots.
So it's 3. So it's 3.
Why are you putting one to five?
It's because they're A squared. These are both sides.
I don't have it memorized, but
Is this part of here? I know this is part of here.
let me see, maybe you guys are right, maybe I'm just right.
I kind of flew through it. Oh, that might make a little difference, I don't know.
That's if you're doing like,
Mike,
like if it's like
again?
Because if you see, okay. So it's
So did you get us up with 2.68?
yes. That's what it's squared. Yeah, so it's
Oh, I knew that there
so A is
That's
not
where I think something is wrong.
What do you get for the Y value?
The one next slope was 2.68, I knew that was on it.
I'm almost 100% guaranteed wrong.
This is wrong.
I'm 98% sure.
It should be at 1.68. Yeah, try putting in the 0.5 again. You lost something, you just got 1.7.
yeah.
You know what, I'm just gonna try to get through and find out where.
There we go, try again.
Oh, so I just think, yeah, I know.
Wait, you just, oh, okay, I got it, okay.
Yeah.
All right, so this is your 1.5, right?
She was like a Los Angeles. Yeah, or I think it's more like they took a picture, right? Like you wrote his name on the pad, and then I looked into the song called Ultra Lightbeat. I think it's
Oh, you know, yeah, he like feeds those things.
yeah. So I think
Chances or times of chances of fail too.
yeah, he actually really likes it. Yeah,
I mean, I'm sorry.
It's gonna be great, Ultra light.
Ultra light.
Ultra light.
Ultra light.
No.
Don't you, please, don't you use the, put like annotations as graphene?
Oh yeah, a long time ago.
You guys did anymore?
Or, still edited, we don't have anything.
What did you
Yeah.
do it on?
I'm getting it every time, I'm not sure what you're doing.
Yeah.
Let me watch it one more time.
You're very good on it?
Yeah, it was like 4 years ago.
It's just a
Yeah,
mess.
I was just not ready to build it.
It's a battlefield I'm losing.
Yeah. Okay, so that's your y value. Okay. Yep. All right. Okay, so when you go through all 4 iterations, and you gotta be very careful, the decimals get really messy, and because of the decimals, your brain can kind of lose your place on what you're doing. It's easier for my brain to process these when everything's nice, happy integers than it is when we get these convoluted decimals, because then I get confused. Which is my y, what's my slope, what am I doing, which do I plug in, right? So be very methodical when you're writing your work for these, right, until you get to the final answer. So how many of you guys made it to, oh, yes, Jessica?
I was just wondering, for each iteration, should we like not round at all, or like?
You want your final answer to be correct to 3 decimals.
Yeah.
Since you're doing some multiplying and some combining of terms, I would go, my comfort level is always 6, mid-problem. If I go at least 6, then I'm okay. If you're dealing with functions with major exponents, you want to go even farther. But for this, since it's just simple multiplying and adding, I wouldn't do much rounding until the very end to make sure that my final answer didn't have rounding error. You certainly don't want to do 3 mid-problem, because then you'll definitely have rounding error by the end, right? So you want to go out at least 4 or 5. I always go at least 6, mid-problem. All right. Are there any other questions? We're going to do more. Don't worry. That was just the first one. Okay. Yay. So anyway, there's another way to do the same thing. You can memorize the following and make a table. This formula is actually the method that you will see in the solution guide by the College Board. So they do the formula. You can go either way. I'm not good at memorizing formulas. It's much better for me to remember the process. So for me, and remember, when you're doing the AP exam, they never ask for more than 2 iterations. So you're not going to gain that much time by memorizing the formula than if you just sit there and do the tangent line equations and plug in. But it's there. So I want you to be aware of it. And it does make the problems a little bit faster. Most of it is just doing what you did in formula form. So the formula says y sub n plus 1, which means the next y, right, equals the previous y value plus our delta x times y prime of, not times, of x sub n, y sub n. So what it really says is take the previous x and y, plug them into your derivative, or your differential equation, times delta x, and then add that y value again. It's really doing what we just did. It's really doing that whole slope, point, tangent line, plug in. It's just writing it out as a formula. So if you want to learn the formula, it's not terribly difficult. It's just, y plus delta x times the differential equation evaluated at xy. And then that gives you the next y value, and then you do the next xy with that formula and plug it in again, right? So with our last problem, I just wrote it out how it would look if we used the formula to do that same problem. So we had, that was our y prime, that was our initial point, and that was our delta x. So if we take the first, like here's our first iteration. So our first x value that we're going to use is, we're going to use the previous xy. So this is like x sub n, y sub n, and then this would be like your x sub n plus 1, right? And we're looking for y sub n plus 1. So our y sub 1, our first y value, is equal to the original y value plus the delta x times you plug the original x and y into your y prime. The next y value you plug in the previous y value plus 0.25 times the previous x and y plugged into your differential equation. Back into the next one. And you just keep kind of doing that until you get to your x value equal 1 and you get your final y value. So that's there. And it goes faster because it's less writing and thinking and equations and that kind of stuff. So it does go faster. So if you want to do the formula, that's totally fine. Right? Whatever you feel like is more comfortable for you. So let's try another problem. Let's just go, we don't have to go all the way to 5 iterations. Let's just go maybe 2 or 3. See if you can go 3. You can use either method. So you can use tangent lines or you can use the formula. Right? Does anyone need to see the formula again? Do you want me to write it down on this page?
Yeah.
Okay. Do you understand this notation, y sub n plus, did you do sequences and series in the past?
Yeah.
Do you remember that a sub n equals a sub n minus 1, like especially with recursive, you get that kind of notation? Okay, y sub n plus 1 equals y sub n plus delta x times, I'm going to put your y prime value into x. Remember, this isn't y prime times, it's y prime of. You're plugging the old xy into your y prime equation. Okay? All right, so your differential equation is ln of x times y. Your original point is y of 1 equals 2. Ooh, they use h. What does h mean? It's the same as delta x. Do you guys remember when you first learned derivatives and you had the definition of a derivative, the limit as h approaches 0 of f of x plus h minus f of x over h? And you also saw problems where it was the limit as delta x approaches 0, f of x plus delta x minus f of x over delta x. H and delta x are used interchangeably. Delta x represents the change in the x value. H also does. In integrals, they use h because h stands for, well, this is my opinion, but I think it's true. H stands for the height of the rectangle, right? So it's that h height, right, that we're talking about when we talk about using that rectangle approximation to get that final exact integral. So I think that's why they came up with h instead of delta x, but they're interchangeable. So when you see h, it's the same thing as delta x. And feel free to call me over, right? If you have questions, if you get stuck, if you want some help. Here, I'll even show you the first one. You got the next slide. Well, did you put, let's see, which iteration are you on? Yes, that's the very first. So x equals, I equals x, right. Oh, this is your tangent line function. Okay, so your first point, oh, your point isn't 2, 1, it's 1, oh, you got it. 1, 2, oh, that's 2 times 1, yeah. So that's your, that's your slope. Shoop, shoop, yes. And that's your first equation, yeah, so now you're ready for 1.2. Yep. Check your progress, make sure you're doing okay. You okay? You're stressed. Okay, so let's see. There's your first equation. Oh, that's a y, okay, y equals. Yeah, and this shouldn't be in the parentheses either, it should be literally a plus. Yeah. Yeah. As long as, do you understand it? Yeah, that's the main goal, is just to make sure you get it. Yeah, you've gotta be so methodical when you're working these. Just the tiniest little dropped negative and it's all kaput, right? So be very careful. If you stopped here, that's okay, because the main thing is to make sure you learn the method, right? If you kept going, your final approximation, if you wanted to get all the way to y of 2, would be 3.172, if you got all the way there. But if you just did up to the first 3 to f of 1.6, you should have had around 2.563. Any questions? Good, let's try another one. Okay, so I went ahead and found one on an old BC exam. So this is the 2009 BC exam, question number 4 from the free response. And here's what it says. It says, consider the differential equation dy dx equals 6x squared minus x squared y. Let f of x be a particular solution to the differential equation with the initial condition f of negative 1 equals 2. Part A, use Euler's method with 2 steps of equal size, starting at x equals negative 1, to approximate f of 0. Show the work that leads to your answer. So they gave you a starting x value, and they gave you an ending x value, and they told you how many steps to use. But they didn't tell you a delta x. So does anyone know what the delta x value would be? 0.5. How do you know? Yeah, 2, so we're going a distance of 1. It's kind of, you could kind of think of it as like that b minus a over n kind of a thing. So we want to travel from 0 to 1 with 2 steps. We're going to go, or from negative 1 to 0. So we'll go by halves. So our delta x is 0.5. So what I want you guys to do is take a minute, try part A. It's only 2 iterations, right? Not so bad. And then, once you get that done, go ahead and do part C. Part B is something you can't do yet. So do part C, which is solving the actual differential equation. the problem written down? I'll go back to the problem anyway. You're right. There it is. This, by the way, was a no calculator question. Did you guys finish part A? Did you get some good points? Or something equivalent? That's the same as 4 1/4. By the way, students who did not have me last term, I'm gonna go ahead and say this so it's on film, and that way you can hold me to it. Numerically equivalent to correct is correct, right? So I actually not only allow, but encourage you to not simplify your numeric answers. So if you left your answer like this, it's not gonna let me write on it, but 4 plus a half times a half, that's fine, right? So, yeah, just leave your answers numerically unsimplified. And there's a reason for this. So the College Board did a study of their past AP exams. And what they did was they kind of categorized the points that were lost in the free response. And they figured out that students lost more points from simplifying their answers than the total of all other points lost combined. So what they put out from that is they actually sent out messages that said, please, please encourage your students not to simplify, because the students who don't simplify actually get a higher score. So if you, I know it's hard to break the habit, but be ready to just leave your answer. You don't have to reduce your fractions, you don't have to combine your fractions, right? As long as your answer is all numerical, you're done. Just stop, let it go, move on, right? And just kind of build that habit. And I always just sit there and evaluate your numbers and make sure that they're equivalent to the correct answer. And as long as they are, they're fine, right? So you can leave an answer 5 plus 6, and you'd be fine, right? You can leave an answer 4 over 2, right? And that's fine. So anything that's numerically equivalent. The only exception to that is you cannot leave an answer in unsimplified trigonometric form. So if your answer is the sine of pi thirds, you can't leave it sine of pi thirds, right? You have to put the root 3 over 2. So you have to simplify the trig, but you can't, but all other numbers you can just leave unsimplified. Does anyone need help walking through part A? Bless you. No? All right, part B, or part C. Part B, Taylor polynomials, we will not get to until chapter 9. But for part C, solving differential equations, you've been doing this for, not years, but for months, right? A month. So anyway, in order to solve, the first thing you have to do is what? Separate those variables. How are you going to separate those? Very good. We're going to factor, right? So you factor that x squared out, and now you can divide by the 6 minus y. Yep. By the way, if part A was worth 2 points and part B is only 1 point, that means part C, solving this differential equation, was 6 points. That's huge. That's a huge percentage of your overall AP exam score on just this one little part of this free response question. So, see how you do. And it has to be solved for y. Yes, very good. Oh, that's the color. All right, so the original point was -1, 2. All right, and we started by house. Okay, so you have your first slope would be 6 minus 2, so 4. So here's your slope. Yep, minus 2. Plug in. You gotta choose that. Yes. 2. 4. Okay. And you got that. And yeah, that's correct. Ooh, let's see. So now, so we use 5, 4.
And then I plug in, would you figure remove the y and then -1 for x, and then you get 4, which is insert there, e to the -4. But this over, did you?
There's 1. Yep.
It's -2 minus 1 0.
Mine is I just added this to my side and divided by x.
Wait.